All right, so this video is going to be on the stereochemistry of radical halogenation. And there's going to be like a tiny bit at the end about the ozone layer as well. So that's some fun stuff. The We did mention before, so if we have a radical compound on a carbon, for example, we will have a p orbital with one single electron in it, and that's going to be sp2 hybridized. It's also going to have the 120-degree bond angles, and therefore it is, trigonal planar. Okay, so this is going to be important because it's kind of analogous to carbocations, right? Or akin to this guy. So remember when we had carbocations for nucleophilic substitution, we ended up with a racemic mixture because that nucleophile can attack from the top or the bottom, and sterics wasn't an issue. It didn't come into play here because it's a planar molecule and the statistical probability of attacking from the top and the bottom was the same. Okay, and so that's going to be the case for radicals as well. If we have these two possible compounds for chlorination of butane, one of them is achiral, and then the other is going to form two enantiomers, but in a 50-50 mixture. So it's a racemic mixture. We have this chlorobutane, 2-chlorobutane, it's an R, and then on the right we have the S. Okay, and again, this is all possible because of the intermediate that precedes this chlorination, this alkyl chloride. So, sorry, I'm struggling to draw the best geometry. I don't like that. I should make it look like the above compound, but I don't want to, so I'll struggle a bit. No, let's do this. Let's just draw it all flat. Okay, so that is the intermediate, and that carbon is the sp2 hybridized carbon, so it's planar. Okay, so it looks like the one above. All right, and that's why we have equal amounts of the 2-chloro butane, the R and the S configuration. Okay. All right, now let's get some practice in, or not some practice. Let me do a couple examples for you so that you kind of grasp the idea. So the concept is pretty straightforward and is pretty similar to stuff we've done before. So if you want to just write out these compounds, I'll give you 4 of them, and then you can draw the product after we do a bromination. Okay, so draw basically all the compounds, and then we'll go ahead and identify which ones are have stereogenic centers, which ones are chiral, achiral, etc. So go ahead and do that, and then pause the video and then come back. It's going to take a while. So let's say we substituted the hydrogen for the bromine there. Okay, since that intermediate would be planar, we can throw the bromine on the other side, right? And so we're attacking that original stereogenic center, and then we're making 2 different enantiomers out of it. Then we can replace another hydrogen. If we replace a hydrogen that's on a carbon that would eventually be stereogenic center, then we have to make sure that we use the wedges and the dashes for the bromine and give us those 2 enantiomers, okay? And after that, we've got a couple more here. So when we put the bromine on the terminal position, that's not a chiral center, so we don't have to draw the wedges, and we should be done. So let's star all of the stereogenic centers. Those 2 guys are just going to be enantiomers, right? Because all we did was swap. We inverted the stereochemistry. These 2 compounds right here, I got to change that to a BR. They each have 2 stereogenic centers, and they are inverted only at the stereogenic center where the bromine is. And so that means those are going to be diastereomers. 2 stereogenic centers here, but these 2 compounds are just completely different because the bromine is on in a different position. Okay, and you can test this by nomenclature. All right, so hopefully you got those. This one right here, we do have to note that there's symmetry in this molecule, right? So that central carbon has 3 ethyls coming off of it. So we're very limited as to where we can put the bromine. So we'll put it here at this tertiary alkyl halide is what we're forming. And then to draw it again and again, so I'm going to get lazy. I just like how pretty it is. There you go. It looks like a bird carrying like a snack or a stick. All right, so the bromine's there at the tertiary position. We have the bromine at the secondary position. I'll make it a wedge and then a dash because that is now a stereogenic center. Okay, and so that means we got two of those guys. Let's go ahead and throw this guy here. We have one more position that we can add that bromine that would create a different compound. And so that should be it for that one. Let's just double check. There's our stereogenic center here and here, and everything else is gravy. All right, so those, again, these two are different compounds. They are achiral as well. So let's try this cyclopropane compound. This one's interesting, so buckle up, because once we start adding stuff, then it gets wild. So if we have just a bromine at this position, you can draw a wedge and a dash, right? But is it really going to be a different compound is what we really need to identify. Okay, so if you're slick, you can just see that they are the same. If you just rotate one of them, they'll have the orientation the same. So they're both achiral. You can also see that there's a plane of symmetry. It would be slicing the methyl and the bromine in half. And so the way I've drawn it isn't exactly clear. If you need some clarification, let me know. Okay. But then we've got a couple more spots that we can do. So there's the bromine with a wedge, right? There's a bromine with a dash. Okay. So think about this though. If we do have those stereogenic centers, does that affect anything else in the compound? And there's really nothing else except for that methyl, right? So let's see if we can add wedges and dashes to these methyls, or let's just draw a wedge for now, and then see if that affects the compound. See the result of the stereochemistry or anything like that. So we will draw the bromine on the bottom now. Still keeping that methyl as a wedge, just because that's how I kind of create things in my brain to make sure I get all possibilities. I like to leave as many things the same as I can. So we have two stereogenic centers in each of these, right? Now, what we want to do is try and figure out how many stereoisomers are possible if we have two stereogenic centers, and that's 2 to the n, which is 2 to the 2, which is 4 possible stereoisomers. And we do have 4 things drawn, but we don't know if these are 4 different stereoisomers, because that's actually 2 to the n is a maximum number. It doesn't always mean you have to have 4. You could have less. It's just a max. So let's rotate this guy, and we've got the methyl as a dash now. The reason why I want to do this is because I want to make this compound look like the first two on the right. Okay. And we'll do that to the other cyclopropane compound. And that's going to look more or less the same, except the bromine is now going to be a dash. Okay. So you may or may not be able to identify the similarities, but these two bromines are dash and those two bromines are wedge, but there's a difference at the methyl position, right? And so how does that affect the stereochemistry, or the relationship, I should say? So let's check out this guy, and we'll compare it. So those pink squared ones are the ones with the check mark, and then we want to compare it to the other ones, okay? So what we want to do is look at the configuration. So bromine on the left, that's an R configuration, okay? And since we have the orientation the same, that means that any bromine at that position with a wedge is going to be an R, and then that means inversion about the stereochemistry gives us S. So that's why we can easily jump to the S configuration for those dash bromines. And then we figure out the methyls are R when they're dashed, and then they're S when they are wedges. Now let's write them all down. We have an RR and an SR. We have an RS and we have an SS. Okay, so now we can clearly see that those are all different, right? So the RR and SS, the relationship is that they are enantiomers, because we have inversion of stereochemistry on both of them. The SR and the RS are both enantiomers, as well. And then the RR-SR relationship, those, as well as the RS and SS, that relationship is also that they are diastereomers. Okay, because we only had inversion at one stereogenic center, the other one remains the same, and so by definition, that's going to be a diastereomer. I know we moved fast on that, but that's because we already know this stuff. So you can also pause the video and or look back on it. But moving on to this, pentane. We have a terminal bromine. We have at the secondary position, we have a bromine, which is now chiral. So we got to throw a wedge and a dash there. And then we have the central position. That central position, again, is a bird holding onto a bromine, right? And so there is symmetry. If you just slice it right down that carbon and the bromine, that is therefore an achiral compound, and we don't need to draw a wedge or a dash. Okay, so we just have those two stereogenic centers on the upper right. That's pretty much it for these compounds. So I do want to, since I didn't really do it on the other ones, I just kind of wanted to, at the end, just show you really quick, like how do you get a stereogenic center or this particular compound in pink, right? So let's go ahead and draw the mechanism more or less. So we've got a super cool lightning bolt of light. That's our HV. It shines on the bromine, and that splits it up, right? So that's the initiation process. It forms a radical or two radicals. And now we've got our awesome propane or pentane, and we swoop on that hydrogen atom. Now what that results in is a carbon radical, which is sp2 hybridized and trigonal planar. Okay, so sorry, I'm struggling with these bond angles real quick. All right, it doesn't have to be perfect. Those are there just because I really want to focus on the radical carbon. Okay, so the carbon can be on the top or the radical can be on the top of the bottom. Okay, so that radical is then going to react with a elemental bromine to form the alkyl bromide, shown here, as well as another bromine radical. Now this bromine radical can go back, swoop on another hydrogen atom on pentane, and then repeat the process. That's the propagation step, right? So I want to, let's go ahead and draw this. I want to show you, this is the way that particular orientation would give you the other enantiomer, right? If you had that electron in that position. But it's even more important that you know that this p orbital with the radical in it can be on the top or the bottom. The radical, there's two phases of that p orbital, and so that p orbital just represents a probability density. So this is just like a probability that you will find the electron in this region, and I think it's like a 90% probability that the electrons resides in that spot. And so it's really in both places. It's on the top and the bottom. And so I don't want you to get confused thinking like it has to be on the top or the bottom, because it's really both. And you may or may not remember, but yeah, orbitals are probability densities. All right, so the ozone layer. So I guess what I wanted to say about that is that you can draw one orientation and just have the radical attack below it or above it to give you the two enantiomers. Sorry. Rather than changing the wedge and the dash. Okay, so Stereochemistry podcast is actually something I want to suggest you listen to for the cool topic, the ozone layer. So episode 25 in 2019, it's called It Was Like Bam, Half the Ozone Layer over Antarctica was gone. And this is basically about the journey that a few scientists went on to determine that chlorofluorocarbons, or CFCs, were destroying our ozone layer. And so real quick, just some radical chemistry, because that's why we're talking about it. O2 plus an oxygen atom creates ozone and heat. Now, ozone's actually toxic for us down here, but it is in our stratosphere. And when ozone is in our stratosphere, it absorbs HV or H nu. It absorbs UV light and creates O2 and oxygen atoms again. And it absorbs about 98% of the incoming UV, right? So imagine how important that is to prevent skin cancer or the destruction of our plants and crops so that we can actually eat. So it's super important, and the fact that it was on its way out was terrifying for a lot of scientists that really knew the significance of ozone. Now, the decomposition of ozone and CFCs, how did that happen? Okay, so CFCs are like a refrigerant, and they're super useful, but and they're also fairly inert down here. But once they make their way up into the stratosphere, they can react with light to form two radicals, CFCl2 and chlorine radical. So look at this. So this is a sigma bond, or it's just an organic compound, right? And then we have two radicals forming in the presence of light. So what is this? What kind of step is this for a radical mechanism? This is initiation. Okay, so the initiation process has occurred. We created two radicals that can go do stuff now and wreak havoc. How does the ozone get depleted? Well, a chlorine radical can react with the ozone to form this ClO radical, okay? And then we also form oxygen. I mean, oxygen's cool, but it doesn't protect us from UV light. And this ClO radical can react with another oxygen atom to create Cl dot, again, another chlorine radical, as well as oxygen. Okay, so now really what's really going on? Well, let's take a look at these materials. We have a chlorine radical coming in, destroying an ozone molecule that protects us from UV light to create ClO. That ClO then reacts with an oxygen atom, which is used to create ozone, which helps protect us from UV light. And then it creates another chlorine atom, right? The chlorine radical, which then can repeat the cycle. Remember? Oh, no. Do you guys watch Friends? Chandler Bing. Fantastic show. Stands the test of time. So, as you can see, one chlorine atom can just wreak havoc on tons of ozone molecules, and not cool, because that's why it went away. It's still in the recovery process. So HFCs and HFOs, these are hydrofluorocarbons and hydrofluoroolefins. Olefins are basically just alkenes. And these alkenes and the hydrofluorocarbons, they decompose before they reach the stratosphere. So our ozone is protected. But I don't know, it always makes me wonder, what are they decomposing into? What's that thing doing? It's probably not good, but so we're just fixing one problem and creating another, possibly. I've never done my research on the effects of those byproducts, but hopefully we don't find out anytime soon, because I think we've dealt with enough this year. Hey, bye.